Hi everyone, this is the first video for section 9.3 on real numbers. So we're finally here. We've worked up all the way throughout the semester, whole numbers, natural numbers, integers, fractions, rational numbers, and we are finally at real numbers. So this is it. This is the last thing we talked about. We built all of the things from the semester to this one point, and that's awesome. So what are the real numbers? So we talked about it a little bit in some of the previous videos for chapter 9, where we have the real numbers. We have this exact same little graphic here, right? We have that the real numbers were all of the numbers that we know and love, the rationals, the integers, the whole numbers, and the natural numbers, along with these irrationals, right? Things that couldn't be written as a fraction of integers. So a formal, very, very formal definition of the real numbers, it's the set of all numbers that can be written as a decimal. And we use, this should be blackboard bold. So we use this R. I'm gonna write that better. So we use this R. Blackboard bold R to denote this set of real numbers. We've talked about that previously. So I'm just gonna go ahead and write down all of the symbols that we use for all of our number sets. Okay, so we have the real numbers, anything that can be written in decimal form. Another way of thinking about this is it's all of just the number line. Anything you can find on a number line is a real number. The reason we define it like this is that whenever you get into more complicated types of math, you start, if you ever took pre-cal in high school, I think pre-cal is where you start talking about imaginary numbers, which are whenever you just extend the real numbers, you start talking about imaginary numbers. And so that's why they're real, because the other ones are imaginary. These are the things that come up more naturally, right? The natural numbers are the most basic you can get, the things you can count on your hands. But the real numbers are just things that we deal with in real life. We never find things that don't really occur in real life in the real numbers. So remember that rational numbers are just fractions of integers. So that means that anything that cannot be written as a fraction of integers is irrational. So again, we have our classic examples of this: square root of 2, pi, the number e, right? This is 2.718281828, repeating. And you can see that this is almost a repeating decimal, but because of that 7 in the front, it's not. At least I'm pretty sure this is what e is. I just know it off the top of my head. Yeah, so all of those special numbers we talked about, pi, e, golden ratio, phi, all of those are in here. So, and remember, you can if you want to, but again, this is not standard by any means, denoting it with this I. You have to be really careful that it doesn't look like the Roman numeral 2. Okay, so again, because we had an alternate definition of the rational number as a decimal, the decimal form terminates or repeats, we can take the converse of that to say a number is irrational if the decimal form does not terminate and does not repeat, right? If we have P or Q, yes, P or Q terminating or repeating, the converse is not P and not Q. Sorry, not the converse. The negation is not P and not Q, not terminating and not repeating. And a lot of times in English, when we say not and not, we say neither nor. It's just a common way to say that in English. So we have this relationship. So it may not be all that clear to you why the square root of 2 is an irrational number. But if you've looked in the book, like you should have, you'll see that they have a proof, similar to how we did a proof of -1 times -1 is +1. They have a proof of why the square root of 2 is irrational. Very classic thing, really, really common. So go look in the book in page 349, to read and understand the proof showing the square root of 2 is irrational. It basically goes by, we assume that it's rational, and then we see something that can never happen. So it's a little bit complicated. So it's something that's not included in any K-12 classroom, and you'll see a little note saying that. However, although we are learning math for the K-12 classroom, you are all still college students, so you should be able to read and understand this proof. If you have questions about it, you should ask me about them for sure to understand it. And if enough people ask, I might make another video that talks about it. Yeah, so go read that example. Example 1, page 349, shows why square root of 2 is irrational. Okay, so we're going to talk about the last properties of things that involve the real numbers. So in the last video, we talked about how the real numbers were closed, right? We had the closure property of the real numbers, means that if we add, subtract, multiply, or divide any two real numbers, we get another real number back. We also saw that the rationals had that property. So we can also say a set is dense if between any two numbers, there's another number of that type. So this is where thinking about the number line is really, really helpful. So we can, again, look at and see, are the naturals dense? Are the wholes dense? Are the integers, rationals, irrationals, and reals? Which of these number sets are dense? So again, I'm going to kind of cheat and use the symbols of them just because it's not what's next, because it's easier than writing it out. Q, I, and R. Okay, so these are the number sets we're looking at. So when we're thinking about the naturals being dense, remember that if we use our list notation for natural numbers, the list of natural numbers is 1, 2, 3, 4, 5, 6, 7, and so on, right? The smallest two numbers that are natural numbers are 1 and 2. So let's just look at 1 and 2. So is there a natural number between 1 and 2? Remember, a number set is dense if between any two numbers, there's another number of that type. So between 1 and 2, is there a natural number? Well, no, there's not, right? If you're just counting things on your fingers, between holding up one finger and two fingers, there's not another way you can hold up between 1 and 2 fingers and still be a natural number. You could hold up 1.5 fingers, but that's not a natural number. So the natural numbers are not dense because there is no natural number between 1 and 2. Okay, no natural number between 1 and 2. So what about the whole numbers? So the whole numbers are just the natural numbers, and then you add on a 0. Well, again, 1 and 2 are whole numbers, and there's no whole number between that. So the whole numbers are not dense. And it's the same reason as the natural numbers. Okay, what about the integers? Again, we can look at 1 and 2 as integers. And the integers, well, there's no integer between 1 and 2. So again, the integers are not dense for the same reason as the natural numbers. And we saw this whenever we were talking about the notion of closure. We looked at 2 minus 3, or 2 over 3, right? When we were looking at that these number sets being closed under division, 2 divided by 3 was not in the natural numbers, the whole numbers, or the integers. And so therefore it wasn't closed under division. And we use the same example for these 3 number sets. And it makes sense because, as we see in our graphic up here, these number sets build on each other. So it makes sense that if they have the same numbers in them, then we can use the same examples. So now we're going to look at the rational numbers. So the rational numbers, is there a rational number between 1 and 2? Well, yes. It's 1/2, right? So between any two numbers, well, between 1 and 2, we have a rational number. And you can actually do this for all rational numbers. There's a fraction that is between it, between two rational numbers. And so you can see that like so. So these are dense. So I'm going to show you over here. So if we have a fraction, a over b, and we have another fraction, let's just assume that we already gave them the same denominator, c over b. So if we have two fractions with the same denominator, right, this form should look kind of familiar to you. We compared fractions like this in the chapter 6 homework. So if we have these two fractions, well, and we have that a is strictly less than c. Well, we know that these are the same as 2a over b over 2b and 2c over 2b, right? These are equivalent fractions. And so we want a fraction to go between them. Well, since a is strictly less than c, we know that, just think about an example. You can kind of have motivating examples. So if a is 2 and c is 3, well, 2 times a is then 4, and 2 times c is then 6, and there's always going to be a number in the middle. So as long as a and c differ by at least 1, there's always going to be a number in the middle when you double them, right? 2 and 3 double to 4 and 6, and there's a number in the middle. 7 and 8 double to 14 and 16, and there's a number in the middle. So always this number in the middle is going to be 2a plus 1 over 2b. So you can always find a number in the middle because of just the way the numbers work. So you can always double it, right? So multiply the fraction, get an equivalent fraction by multiplying by 2 on top and bottom, and then add 1 to the numerator or subtract 1 from the numerator, depending on which side you want to do it. So like 2a plus 1 or 2c minus 1, you can put that number in there and it'll always be in the middle. Okay? Similarly, you can do a similar thing for irrational numbers. So these are also dense. So you can think about irrational numbers. We just think of them as decimals that are all not repeating, and not terminating, correct. So these are not terminating and not repeating. So for example, you can look at any irrational numbers, and there's always going to be a number between them just by changing the decimals. So I'm going to write it up here because I don't have a lot of space. So I'm going to box this in. And this is showing, well, I'm going to write a less than c. Okay, so what does this show us? This showed us that Q is dense. And then I'm going to go up here to show that I is dense. So I'm going to give you an example, and you can do the same thing for any example. So you remember the example that we had of an irrational number. We just made up 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on. So if we have this irrational number and we have something that's really similar, we have 0.0100 10011, and we want to know what's between these two numbers, we can do that just by, first off, expanding the numbers. Let's see if this one was then 0001 and this one was then 0001. We could find a number here in the middle. I'm going to write it in black. So essentially, when you just look at these two things, you're comparing 10 and 11. and the things that come right after that are different, right? Because then we start off with, there should be another 0 up here. Then we have things that look similar. Again, they only differ in this one spot. So we're comparing 10 and 11. What's between 10 and 11? 10 and a half, right? Or similarly, you can think about it, as comparing 100 and 110. And that one's a lot easier to see what's between them. What's between 100 and 110? 105. And then we continue with 0, 0, 1. And then they just repeat. So it's actually not too difficult to find a number between any two irrational numbers. You don't need to know how to do this. You just need to know that it's true. But in case you are like I was in school and wanted to know why everything was true, here's an example to show you that you can do it. And you can even take any irrational numbers you want and see that you can do this. I showed you a more general way for Q, but here's a more general way to show that Q is dense. You again can check it yourself with any numbers you want. This will always work. Okay, so because Q is dense and I is dense, and we know that the rational numbers are just the union of Q and I, this tells us that R is dense, because we know that between any two rational numbers is another rational, and between any two irrational numbers is an irrational. That means that R is definitely dense if those two are. Between any two real numbers, remember, any real number is rational or irrational. There's going to be another one that's rational or irrational. Okay, so this is the density property. So again, I'm not going to ever ask you to find anything that's too complicated about a number between, like this one up here, that I was dense up there was a little bit complicated. But yeah, so just know what this is. But again, thinking about it in the number line, you can really think of this density property is if you zoom in on a number line. So this density property is just if you zoom in on a number line, you can always find another number that's real. You can always find a number that's rational, irrational, or real, because those are the things that are dense. But if you zoom in on a number line that just has whole numbers, natural numbers, or integers, well, you're only going to find those things, only those numbers. Okay, so this is it for the density property, and that's it for this video.